To test the impedance of a transformer, two methods are available. Firstly, the voltmeter-ammeter method, and secondly, the short-circuit method. For the voltmeter-ammeter method, you will need a voltmeter with a 100-volt scale, an ammeter with a 1-amp scale, a variable AC power supply, and a resistor rated for high current. The procedure is as follows. 1. Connect the transformer's low voltage terminals to the power supply. 2. Connect the low voltage terminals to the resistor in series. 3. Connect the voltmeter across the resistor. 4. Connect the ammeter in series with the power supply and the transformer. 5. Gradually increase the voltage from the power supply until the current reaches about 0.2 amps. 6. Record the voltage in volts and the current in amps. 7. Calculate the impedance in ohms using the formula impedance equals voltage divided by current. For the short-circuit method, you will need a short-circuit connecting device such as jumpers or copper bar, a wattmeter, a voltmeter, and an ammeter. The procedure is as follows. 1. Connect the transformer's low voltage terminals to the short-circuit device. 2. Connect the wattmeter, voltmeter, and ammeter to the high voltage terminals. 3. Apply voltage to the high voltage terminals and gradually increase it until the current reaches a safe value such as 10% of the rated current. 4. Record the voltage in volts, the current in amps, and the power in watts. 5. Calculate the impedance in ohms using the formula impedance equals voltage squared divided by power minus current squared multiplied by lead resistance, where lead resistance is the lead resistance of the transformer. When conducting these tests, it is important to use safety precautions, as the equipment can handle high currents and voltages. Ensure that the test setup is properly grounded. The results will be affected by the accuracy of the equipment and the test setup. Remember that impedance is a measure of the opposition to alternating current, similar to resistance in a direct current circuit. It's a crucial parameter for understanding a transformer's behavior, especially under fault conditions or when matching it to a specific system. The voltmeter-ammeter method is simpler but generally less accurate than the short-circuit method, particularly for larger transformers. The short-circuit method, while requiring more equipment, provides a more realistic representation of the transformer's impedance under load. When performing the voltmeter-ammeter test, the resistor is used to limit the current and provide a voltage drop that can be accurately measured. The key is to use a resistor with a known resistance value that can handle the anticipated current without overheating. Choosing the correct range on both the voltmeter and ammeter is also crucial for accurate readings. If the voltage or current is too low, the readings may be inaccurate due to the instrument's resolution limitations. If the voltage or current is too high, it could damage the instrument. In the short-circuit test, the short-circuiting device must have a very low resistance to ensure that the voltage drop across it is negligible. This allows for a more accurate measurement of the transformer's impedance. The voltage applied to the high-voltage terminals should be gradually increased to avoid overcurrent and potential damage to the transformer. Monitoring the current and voltage levels during the test is critical. The formula for calculating impedance in the short-circuit method includes a term for the lead resistance of the transformer. This is because the resistance of the transformer windings and leads can contribute significantly to the overall impedance, especially in larger transformers. The lead resistance can be determined by measuring the resistance of the windings with a low-resistance ohmmeter. It's important to note that the impedance value obtained from these tests is typically expressed as a percentage of the transformer's rated impedance. This percentage impedance is a key parameter used in system protection studies to determine the fault current levels that the transformer can withstand. Understanding transformer impedance is essential for selecting appropriate protective devices such as circuit breakers and fuses. It also helps in coordinating these devices to ensure that they operate correctly during fault conditions. The impedance of a transformer affects the voltage regulation, which is the change in secondary voltage from no load to full load conditions. A higher impedance generally results in poor voltage regulation. Transformers with lower impedance tend to have higher fault current levels, which can stress the electrical system. Therefore, selecting a transformer with the appropriate impedance is a crucial consideration in power system design. Another factor to consider is the transformer's X/R ratio, which is the ratio of the inductive reactance to the resistance. This ratio affects the waveform of the fault current and the performance of protective devices. Transformers with high X/R ratios can produce asymmetrical fault currents that require special consideration in protective device settings. In addition to the voltmeter, ammeter, and short-circuit methods, there are more sophisticated techniques for measuring transformer impedance, such as using impedance analyzers or frequency response analyzers. These instruments can provide more accurate and detailed information about the transformer's impedance characteristics over a wide range of frequencies. However, these methods typically require specialized equipment and expertise. Regardless of the method used, it's important to follow all safety precautions and to use calibrated equipment to ensure accurate and reliable results. Transformer impedance testing is a critical part of ensuring the safe and reliable operation of electrical power systems. It is also important to ensure the ambient temperature is stable, as the winding resistance changes with temperature. This can be mitigated with temperature correction formulas. For this short-circuit test, the applied voltage should be gradually increased until the rated current is reached or a safe percentage of it. The test should be performed quickly to avoid overheating the transformer. The current should be monitored closely during the test. The leads to the transformer should be as short and thick as possible to minimize the resistance. If the lead resistance is a significant portion of the total, it will reduce accuracy and increase the risk of error. The instrument transformers CT and PT should be of adequate accuracy class. The CT should be selected with the knee point voltage much higher than the test voltage to avoid saturation. A saturated CT would give incorrect current readings. The short-circuit impedance of a transformer is typically expressed as a percentage of the rated impedance. This is the voltage that must be applied to the high-voltage winding to circulate rated current in a low-voltage winding, with the low-voltage winding shorted. This percentage impedance is used for fault calculations. The test should be carried out at rated frequency, as the impedance is frequency dependent. Off-nominal frequency will lead to inaccurate results. If the transformer has a tap changer, the impedance test should be performed at different tap positions to get a complete impedance profile. The tap position will have an impact on impedance. The nameplate impedance value is usually for the normal tap position. If the test is being performed to verify the nameplate value, the tap changer should be in the normal tap position. The results of the impedance test can be used to assess the condition of the transformer windings. Any significant deviation from the nameplate value may indicate winding deformation or insulation breakdown. The impedance test can be used for detecting problems such as shorted turns in the winding, core movement, or loose connections. The impedance test results should be compared to previous test results, if available, to identify any trends or changes over time. A sudden change in impedance may indicate a developing problem. If the transformer is equipped with oil, a dissolved gas analysis should be performed along with the impedance test to get a complete picture of the transformer condition. The impedance test is a low-voltage test. It does not stress the insulation to the same extent as a high-voltage test. It's still a valuable tool. The impedance test is usually performed as part of a routine maintenance program for transformers. It is also performed after a fault to assess the damage to the transformer. Always use calibrated test equipment and ensure that all connections are tight and secure. Make sure the equipment is properly grounded and follow all applicable safety regulations. Before starting the test, inspect the transformer for any signs of damage, such as oil leaks, cracked bushings, or discolored paint. If any damage is found, do not proceed with the test until the damage has been repaired. Ensure the transformer is disconnected from the power system and isolated from any live sources before starting the test. Never perform the impedance test on an energized transformer. Proper testing requires an understanding of the transformer's internal construction and design. Consult the transformer's nameplate and documentation for key information such as rated voltage, current, impedance, and tap settings. A proper understanding will help ensure the test is conducted correctly and the results are interpreted accurately. Consider the effect of external factors on test results, like temperature, humidity, and nearby electromagnetic fields. These can influence instrument readings and introduce errors. Wherever possible, control or compensate for these external influences. Employing shielding, temperature correction factors, and averaging multiple readings can help minimize their impact. When interpreting impedance test results, be aware of acceptable tolerances and variations. Transformer impedance values can vary slightly from nameplate values due to manufacturing tolerances and aging effect. Consult industry standards and manufacturers' specifications to determine acceptable ranges. Significant deviations beyond these ranges warrant further investigation. Compare impedance test results with other diagnostic tests such as insulation resistance tests, turns ratio tests, and oil analysis. A comprehensive approach, incorporating multiple testing methods, provides a more complete picture of the transformer's overall health and identifies potential issues. Finally, maintain detailed records of all impedance tests, including date, time, environmental conditions, equipment used, and results obtained. These records serve as a valuable baseline for future comparisons and trend analysis, helping to track transformer performance and identify any signs of deterioration over time. The data you record and save will make troubleshooting easier. Understanding the specific needs of the equipment combined with safety will create the best possible testing environment.